Hi everyone, welcome back to a third week of Chem Lab. Today, or this week's lab is going to be particularly more involved, a little bit longer, and this is kind of where we start to really get into a little bit of chemistry. And so we're going to be looking at the limiting reagent synthesis of calcium carbonate using gravimetric analysis. So I'll go through an overview of the PowerPoint, and we'll start with updates and assignments. For next week, um, what I want to say is that you should be able to finish everything in this lab ready to turn in for next week, except for the percent yield calculations. So really what I'm getting at here is just make sure that you have everything ready to go so that when we come into lab, we weigh our product and then we plug that number into our percent yield calculation in Excel and in our Word document. And so you should have everything ready. And so that way we can just plug that number in and submit the lab within the first 15 minutes. I don't want to take too long next week at the beginning of lab. So you won't be able to submit it before, but just come prepared. And then, of course, our pre-lab quiz on next week's topic. So this week's safety topic is waste disposal. It's very, very important in chemistry because obviously we work with a lot of different kinds of chemicals. A lot of things seem like they could go down the drain, but that is not the case at all. So just be cognizant. If you're not sure, ask me, ask the TAs. Definitely when we get to organic chemistry lab, you'll have a lot of chemicals that have to be properly disposed of, more so than in Gen Chem. But in Gen Chem, especially this week, this is the first time we're actually going to be collecting waste. We have carboys in waste carboys in the fume hoods for liquids and then for solids. So this is our solid waste. We'll just pop that open, put in kind of solid waste in there, and any liquid can go in these carboys. So let's please keep that in mind. And then, yeah, what I would do here, I guess this is recommending you to just collect everything in a big 600 ml waste beaker and then transport it to the carboys as opposed to just going back and forth multiple times. Just kind of, it's more efficient. Just make sure that any solid gets placed in the solid waste bucket by the whiteboard, and then rinse any glassware and make sure that you um, return everything as it was. Okay, so now let's go into a little bit of a background and before we dive into the procedure. So gravimetric analysis is simply just determining an amount of analyte through measurement of a mass. So we'll be using our balances again. So by this point, you should be kind of familiar with them. But before we really dive into the procedure and the goal of this lab, and again, forgive me for taking a little bit longer on this PowerPoint presentation. It should be slightly longer than the last 2 weeks. But I want to make sure that I cover a lot of the topics that we're going to see because I don't know where everyone is in lecture. So one of the first things we want to talk about is limiting reagents. And there are so many good examples that we can use for discussing limiting reagent. But one of my favorite is discussing limiting reagent in terms of creating bicycles. And so if you're a bike shop and you have several bike parts, let's see how many bikes we can make with the bike parts that we have. And so the top row here are just wheels. What I'm drawing here are supposed to be handlebars, but they're horrible handlebars. And then the frames, let's say, I don't know, horrible frame, right? But let's say that's what I want so that we can have something like this. And that's our horrible, hideous looking bike. But the point is, we want to make a bike, but we have a lot of parts. So our limiting reagent will only allow us to make a certain number of bikes. And so while we have excess number of parts and some of these are in excess, it doesn't matter because we can only make as many bikes as we can as our limiting reagent allows. So in this case, if we look at the wheels again, let's start with the wheels. We have one set of wheels. We can make one bike. We can make two bikes. And we can make three bikes, right? So we can make up to three bikes. Oh, let's look at the handlebars. It just so happens that we can make 1, 2, 3 bikes as well. But we only have 1, 2 frames. So we can only make up to 2 bikes because we only have 2 frames available. And so that means that our limiting reagent has to be our frame. because we can only make as many bikes as our frames allow. So this can be kind of incorporated into chemistry as well. When we look at reagents, we look at moles, and we can determine our limiting reagent based on the moles of reagents. And so keep this in mind. It's not going to be based on grams because different compounds have different molecular weights. Otherwise, that would be too easy. Instead, we're going to look at moles. So remember, maybe keep in mind that calculation of going from grams to moles, moles to grams, using that molecular weight of that specific respective compound. So use moles, not grams. Okay, so the goal for this lab is to determine the yield for 3 reactions between, well, actually, I should take that back. It's the same reaction. We're just going to do it 3 times. So the reaction is a double displacement reaction, and you can see here sodium carbonate, then goes to sodium chloride. And then, of course, our calcium chloride gets converted into calcium carbonate. That's why it's a double displacement. It gets displaced twice. And so what we're going to do is we're going to do this reaction 3 times, but with different amounts of starting material. And so that's why we're going to have this. Of course, if we have different amounts of starting material, we will potentially have different percent yields. And so we'll dive into the math here in a little bit behind that. But, we just talked about limiting reagents, so keep in mind what the limiting reagent will be for each reaction. It will change since we will be using different amounts of starting material. Now, one thing to note, this is very important, any kind of stoichiometric conversion that we'll have for the rest of this PowerPoint and this specific lab, this will be a 1-to-1 ratio. And what that means is that there's going to be a 1 molar ratio of starting material to product. Not our byproduct. That's a 1-to-2, right? Because there's a 2, 1-to-2. That's not what we care about. We care about our product here. So 1-to-1 ratio, 1-to-1 stoichiometric ratio. So no need to multiply or divide by 2. So we'll keep that in mind. It makes our life easier. Okay, so let's go through a quick calculation practice problem. And in this case, we are asked, this is a different compound that we're not going to work with, but it's just an example. A student weighs this amount of Allura Red, and then this person transfers it to a 500 ml volumetric flask, and then fills it to 500 milliliters with DI water. Here's a question. What is the concentration of this solution? Well, in order to determine this, we of course need the molecular weight of the dye so that we can convert to moles. Now, let me see. Yeah, I guess it is over here. So really the biggest formula that we're going to be working with here, really the only one, I guess, is this formula right here, where we have molarity, which is concentration, capital M, over, equals moles per liter. Moles per liter. And so that's concentration, which is the same thing as molarity. And so let's keep that formula in the back of our heads because we're going to use that a lot. So in this first step, what we'd like to do is calculate the moles of solute of Allura Red. Well, remember, I told you that we need the molecular weight to calculate moles. And so in this case, we're given this number. We're given 0.03 grams. And so in order to get moles from grams, we just need to divide by the molecular weight because we see that grams and grams will cancel out, leaving moles at the top. And so that way our final unit should be moles. So we divide 0.03 by this number, and we should get this number here. And of course, that's going to be the numerator that we need. Good to go. Well, now let's see if we can't figure out the bottom. And so in this case, what we want is we have volume already, but we have 500 milliliters. Remember that our formula requires us to be in liters, so we just need to convert. And if you remember your prefixes, milli is 1,000, so we just need to divide by 1,000. And so 500 divided by 1,000, because there's 1,000 milliliters in 1 liter, and we need these two to cancel out. So if we put this above this, then those millis cancel out, and you're left with liters. And so that should give us 0.5 liters. So now we've got liters of solution calculated. So now that we've got both parts, we can go ahead and put them into that formula, plug them in. This is from the first step. Second step, we just divide that by 0.5, and we have the number of moles. We can simplify this too by saying we can divide this by 1,000 and say 121 millimoles as well. Or sorry, 0.121 millimoles. Because again, moles per liter is just the same thing as molarity, right? Capital M. And then I just moved this decimal place over 3 times and added the milli. All right, so in terms of then actually weighing out the compound, this person goes ahead and you're going to do something similar, puts the weight paper on, tears it, and then adds the 0.03 grams of a liver red. So you're going to do something similar. Then after that, you're going to transfer your compound into a 500 milliliter volumetric flask. So this is what a 500 milliliter, it says 1,000, but ignore that, same thing. It's a 500, it's a volumetric flask. So the first thing you'll do is you'll add your compound in there, and then you'll fill it up halfway with BI water. You don't want to go above halfway first, because what you want to do is you want to swirl that. Otherwise, if you fill it up, you won't have any room to swirl. And I believe that it says to invert as well. Let's stick to swirling first in case that some of our caps aren't secure. And then hopefully that works really well before we even try inverting. But let's fill it up to halfway, swirl around a little bit, and then add the rest. And there's this line right here that's etched in the glass that indicates exactly where 500 milliliters is. So keep that in mind. You can't see it in this picture, but it will certainly be on the volumetric flasks. Okay, I'm going to do that. Okay, so this procedure, we're going to do this in groups of 2. So work with your lab partner on this. Now, what we're asked here is slightly different from what we just encountered, where we were given a certain amount, a certain mass, and then asked to calculate the concentration. Here, we are given the concentration, and we're asked to determine the mass. So we're just slightly working backwards, but we're given the volume both times here for both of these compounds, sodium carbonate, calcium chloride. And so remember this formula. Sorry about that, let's see. Capital M is moles over liters. Well, look at this, we have moles, right? We have 0.2 molar, or sorry, not moles. 0.2 molar is equal to 100 milliliters. Well, we need that to be in liters. And I'll go over the math again in the next slide, but we can just do 0.1 L, and then we're left with moles. It's a simple conversion, right? And then from moles, we can go to grams, and then, weigh it out. So let's look at that. So the first thing that needs to be done, of course, is first calculate the moles of solution, or solute. So if we want to calculate the moles of solute, we, of course, need the molecular weight. And so, kind of what I just told you already, we have 0.2 molar moles. We don't have, that's what we're calculating, and of course we have 0.1 liters. And so that can just be seen here, where I'm converting 100 milliliters using 1,000 milliliters per 1 liter, and that gives me 0.1. And then I rearrange this formula to solve for moles. So that should be 0.2 times 0.1 equals moles, and that should be 0.02 moles. Okay, so at this point, if we have the moles, make sure you write this number down because that will be important. Any moles that you determine, as well as mass, you'll need to know those for later, so write those down. To convert moles to grams, we need moles to cancel. So of course, if we have a mole in the numerator, we need a mole in the denominator, and they will cancel. And so of course, here in this case, we think, we ask ourselves, how many grams are in 1 mole of sodium carbonate? Well, that can just be simply found by looking up the molecular weight of sodium carbonate. And here we're given the weight as 105.99 grams per 1 mole. So in this case, you just multiply 0.02 times 105.99, and we should get this number that's written there, 2.120 grams of sodium carbonate. Great, now that we've got that number, we can plug this in here, right? 2.120 grams. And now the reason you have calculated versus actual is for specific reasons. So of course we have the calculated mass, we just figured that out. But the actual mass, the reason we have that there is because it's very unlikely that we will weigh out when we go to the balance and try to weigh out exactly 2.120, it's very unlikely that we're going to land exactly on that number. And if you do, great, good for you. But it's more likely going to be, I don't know, let's say you scoop it out and land on 2.2, right? 2.20, whatever it is. And if that's the case, don't worry about getting exactly 2.12. We don't want you to scoop out of that container and put anything back in there. So just whatever, unless it's just a ridiculous amount, then we'll dispose of it. You never want to put back into the stock solutions or to original concentrated powders. So if you get 2.2, great. Write that number down and move on with that number. Now what you're going to do is you're going to do the same thing for calcium chloride, the same thing we just did before. So you'll just find the number of moles and then of course the number of grams that you need for calcium chloride. And you can just pause this here to see how that math works out, and we get 2.220. So we get 2.120, and then we have 2.220. And then whatever this number is, right? Let's say we had 2.3 or 2.1. Whatever we actually get, whatever we actually weigh out, make sure that you recalculate the concentration based on that number. Because like in our original example, if you weigh out a different number of grams than we calculated, that will change the concentration of the original starting material. So make sure you go back and recalculate that. In this case, if you have, I don't know, slightly over, you might have a slightly higher concentration, right? And that will affect the calculations down the road. So make sure you go back and figure that out. Okay, so following that procedure, then we're going to rinse our burettes. So our burettes are kind of like really thin graduated cylinders with a stopcock here at the bottom. And the stopcock stops the flow of liquid when it's parallel to the bench top. If it's perpendicular, then the water will flow, the liquid will flow. And you have 0 milliliters right about halfway. So what you want to do, you'll have two burettes. One burette will be labeled calcium chloride, and the other one will be sodium carbonate. And so what you want to do for each respective analyte, you want to just first rinse it with water. So first, rinse it with water, and then rinse it with that certain compound that you've made. And in this case, we've made 100 milliliters for both, so you should have plenty of solution. So I would just say 10 milliliters, swirl it around, and rinse with the respective reagent. And the reason you want to do that is because you want to get as much calcium chloride or sodium carbonate coating the inside of those burettes. Otherwise, it might be contaminated with other compounds that we've worked with in the past. So you just want to make sure you rinse it with water and then rinse it with the respective solution. And then, of course, then you fill it up above the 0 line. And sounds counterintuitive, but that's again because the 0 line is not at the bottom, but it's halfway or maybe closer to the top. So just fill it up, and then we should be good to go. So then you should have these two burettes ready to go. And then we will look at the reactions. We'll start these reactions. Make sure you don't confuse these. That will, of course, lead to bad results. So in this case, our first reaction, we will have, once you have those two burettes ready to go and filled up, what I want you to do is have 3 beakers labeled 1 through 3 for each reaction. So the first beaker, what you're going to do is you're going to fill it up with 12 milliliters of calcium chloride, and then swirl it around, and then move it over to the second burette and fill it up with 23 milliliters of calcium chloride. So you should have a total of 35 milliliters of a mixture of calcium chloride and sodium carbonate. And then you stir it for 2 minutes and see what happens. You should see this liquid, you should see some solution crashing out into a precipitate. So take a picture of that and then go to the next one. So make sure you stir for 2 minutes on a stir plate with a stir bar. And stir bar it's just like this little tiny pill that you just drop in there, put it on the stir plate, turn it on, and it should stir by itself for 2 minutes. Once you're done with that, move on to the second reaction. So same idea. 19 milliliters of calcium chloride, 16 milliliters of sodium carbonate, so you should have 35 milliliters. So same idea. Stir it, see if that precipitates out. If you don't have 3 stir bars, I would not. I would just probably rinse that first stir bar with water, DI water, into a waste beaker, and then drop it into the second one. And then, of course, do that same thing again for the third reaction until you have 3 beakers. So the next step that you're going to have is that of filtering the solids, because you will have certain reactions that precipitate out a solid. And so what you want to do is use a Buchner funnel. And you'll likely use this a lot in organic chemistry, so maybe this is a good introduction if you haven't worked with one before. With a Buchner funnel, let's see, yeah, here we go. We'll have a vacuum flask, and that vacuum flask will be hooked up to a thick orange hose that's hooked up to the benchtop outlet for vacuum. And you'll have this valve, and you just swing it one way or the other to open the vacuum. And so that vacuum, once it starts, it's a thick hose. Remember, there's a thin one for water and there's a thick one for vacuum. Definitely ask me if you can't find a thicker one. Once that vacuum is turned on, anything that comes to the top will be sucked into the vacuum flask, and of course any air will be sucked out. And so the Buchner funnel is a ceramic funnel that has holes here at the bottom. So what you're going to do is you're going to put filter paper that fits perfectly at the bottom of this Buchner funnel, and you'll just spray it with DI water, make sure it's rinsed, and you'll see once you turn the vacuum on, that water will just shoot out into the bottom. It's a really great method for drying out or isolating any dry products from liquid, from solution. So that's exactly what we want. So for each of our 3 reactions, 1 through 3, especially if we have a precipitate, we will pour that mixture of solution and precipitate into our Buchner funnel. And I would say, I don't know if it gives you a specific time to let it dry, but I would say pour it on there and leave it there for at least a couple minutes, and so that way it dries as much as possible as it sucks air through the Buchner funnel. And then don't do it all at the same time, one by one. So once you do that, for one reaction, what you'll do is you'll weigh a labeled weigh boat, put your initials and the reaction number on it, and store it to the side, because we're going to come back, like I said earlier, to weigh the actual product. We just want it to dry over the next 7 days. So then you'll do this again, get a fresh filter paper, do it for the second reaction, weigh it, store it, and then do it a third time. Do not put all 3 into the Buchner funnel. You don't want to do that. You want to do it one by one, so that at the end of the day, we have, I don't know how big the weigh boats are, but we might have one big weigh boat with 3 filter papers on there, and then we can just label it in Sharpie 1, 2, 3, and of course your initials. My initials are SIS. Or we might have smaller weigh boats where only 1 filter paper fits on each weigh boat. Same idea though. You would label it 1, 2, 3 with your initials. The point is, you want to weigh the weigh boat and label it, because next week we are going to, and remember, there's a whole week of this experiment going on, so you want to make sure that you label clearly, otherwise you won't be able to find your product. So we'll make sure that these dry over the course of 7 days. We'll come back at the beginning of lab next week, and then we'll just weigh them and see what our product is, so that we can calculate percent yield. Let's see, you should have 3 products between you and your partner, of course. Remember where you place your sample, and then we'll address your masses. I would say electronic lab notebook, but just in your Word document and your Excel sheet. And speaking of Excel sheets, you don't have to use this format that's given in your pre-lab or your procedure. instead, I'm going to provide you with an Excel sheet, and it's already posted on Canvas so that you can see what it looks like, and you can kind of get an idea of what you'll be asked based off of this Excel sheet. So in this Excel sheet, it's color-coded so that you have what's given in the procedure, known properties, and then any calculations you might have to do. And so, for example, we've already calculated the moles needed in the previous slides, the moles or the mass needed based on the moles versus the actual mass and the actual moles. So this is where you work backwards. Keep that in mind. And we already did that calculation as well. And so then once you work backwards, these will all be in 0.1 liters. So then you'll just divide that by that. And so you'll plug those numbers in. And then moving down here, these are each of the 3 reactions that are coordinated with the 3 reactions that we are given in table 1 in your procedure. And so in this case, that first reaction, it was calcium chloride was 12, I believe. Calcium chloride is 12 and 23. So then that's given to you already. So 12 and 23. And so you'll just fill that in. Of course, the moles that you add based on 12 milliliters, because you're adding a certain amount of milliliters, a certain amount of volume, you will determine, you will have to change the number of moles because, again, everything comes back to this formula that we've talked about. Moles per liter, right? And so if you have, let's see, a consistent concentration and you change the number of liters, well, then that likely has to change as well. So that's why you need to calculate the moles based on the volume. And same thing here, the moles of sodium carbonate based on the volume. And then, of course, you'll do that for all 3 reactions, so 2 more times. And then moving down, then you will get to the theoretical yield calculation. And again, I don't know where everyone is in lab, or sorry, in lecture, but generally, with the theoretical yield calculation, you always want to go from grams to moles, and then from moles to moles. In this case, it's just going to be a 1-to-1 ratio of starting material to product, and then moles to grams, back to grams of product. And I like to do these one by one, so maybe we can talk about them more in class. But you'll have the moles of the limiting reagent, and that can be seen just based off the moles that you added, right? And so if you have, I don't know, 0.002 and 0.004, well, that's very clear which one is the limiting reagent. So it should be 0.002. And so then moles of calcium in excess, well, because it's limiting reagent, it really should be 0. There's nothing in excess. You could theoretically put a negative there, but we'll just put 0. Versus the moles in excess for the sodium carbonate, well, that's going to be 0.004 minus 0.002, well, that's going to be 0.002. And then the theoretical yield will just be the same, the total amount that the limiting reagent allows, and then, of course, in grams of the product. So then you'll convert the moles, this part right here, moles back to grams using the actual product, which is calcium chloride, I guess calcium carbonate, yeah, calcium carbonate. And that should have a mass. I don't think it's written in here, otherwise you have your masses there. Use those masses, but in case you need it, generally online gives you pretty good numbers. But in this case, we want to use 100.0869 grams per mole for our product. 0.0869. Okay. And then the last thing is our percent yield. So let's talk about that briefly, because that's going to be very handy for the rest of chemistry, organic or otherwise, really. Anytime you take chemistry, you'll need to know how to calculate percent yield. And percent yield is just yield equal actual over theoretical times 100. And so theoretical is the one that we calculated using that conversion, grams to moles, moles to moles, and moles back to grams. And the actual, of course, is what you actually weighed from your experiment. So this is what we will weigh next week. That's why we need to That's what I was saying earlier. We need to just wait on that for next week so that we can plug that number in. But just go ahead and do everything and maybe plug a fake number in there so that when you get that actual number, we can just plug it in and turn it in. And so then all of these will, these calculations are really just the same thing we see in this Excel sheet. I just need you to show your work to see how you got there, but otherwise just plug those numbers, the results into the Excel sheet, but show your work here. But of course, maybe this won't have work that's just going to be a number. So very similar, I mean, pretty much identical to the Excel sheet, but just in the Word document. And then, yeah, same idea actually. And so all you have to do is just maybe do some subtractions and maybe some conversions. But otherwise, nothing too difficult from, at least nothing different from what we've already seen. So apologize for a rather lengthy pre-lab lecture. This will be a slightly longer lab, or at least more involved. But I hope everything made sense. And if not, please feel free to ask questions during lab or before lab, and I'll be happy to answer them as they come up. And ask, of course, the TA is a great resource as well. And yeah, we'll see you guys in lab soon.